But I keep on using, so I keep on hearing no man's sky. I'm like, this project ideas.
Yeah, Kerm and I were talking about that. I mean, no, it isn't.
I don't know how it looks.
It looks like it quickly, but I feel like it'll be fun. Like really fun.
Okay, so let's start. So, okay. Those. No, I don't have any announcements for today. I was looking, I thought I had some, but I don't. That's the other class that's got the announcements. Okay, so our big themes for today are how does an interface or a mobile device or something like that get an IP address? Do all packets have to go through a router? Okay. And how do you find out the MAC address of a machine? Okay. So those are sort of some of the things we're going to be focusing on today. And these are the sorts of things that you should be able to do after. Oh, I do have an announcement. I knew what it was. I put up a new set of learning goals. That's what it was for the next parts. I haven't put up the readings that go along with those, but there are, in fact, additional learning goals being posted to the Piazza account. So today we're going, so these are some of the smaller things we're going to do. We're going to look at DHCP. We're going to look at ARP, which ties back to the stuff on Mac. We're going to look at we're going to look in more detail now at what some of those other layers do as far as routing is concerned that we sort of just touched on briefly. And if we get to the very end, we'll be able to know how we manipulate all the various headers and stuff like that as data goes through the network. And that will lead us into talking about natting routers. Okay. So at the end of Monday's class, or not quite at the end, just a little bit before, I put that map up of all the various excuse me, internet authorities. So I actually went and I looked before coming to class today, and there's a couple spots, and they do in fact claim that the only site, or the only internet authority left that has any IP addresses to give out is in fact Africa. Everyone else has exhausted theirs. So North America was second last to go. And, well, this is assuming Africa is the last to go. Be Africa, then North America, and everyone else has been out for a while. Okay, so some of them have been out since 2011. Yeah. Sorry, just a sec. If you go to the home page of the course, there's a little internet counter on there, and it tells you that information.
Are people switching to IPv6 now, or?
No. No, they're not. So. There's a challenge with switch. Okay, I'll talk a little bit about the switching. We'll talk a little bit about switching to IPv6. Okay, so you guys are probably too young for this, for part of this anyway. So if you go back 20 or 30 years ago, or a little more than that, depending upon where you lived in the world, the telephone system basically sucked. If you were in North America, and I guess some of Europe, but not all of Europe and stuff like that, the phone system was pretty good. North America probably had about the best, I guess. And the rest of the world was, yeah. Okay? And especially if you go to some of the areas in Africa, or sort of what would be now called sort of third world or second world countries, their phone infrastructure was almost non-existent for many of them. Well, if you go there today, their phone system as far as landlines is concerned probably isn't much better. But they have essentially got very good wireless communication because it's the technology was developed. It became relative, and it was a lot cheaper to install that than it was to install wired lines. And so that's what happened. And so they essentially brought themselves up to for lack of a better term, world standards in telephony by skipping a whole generation of technology. They never went the landline route. Okay? So the same sort of issue is sort of coming up with something like IPv6. So IPv6 is not backwards compatible with IPv4. So if you have a router that understands IPv6, there's no guarantee that that router knows anything about IPv4. IPv6, well, whatever, okay. If it knows about 4, it doesn't necessarily know about 6, and vice versa, okay? And it's not like you can sort of say, oh, well, you know, it's just a few more fields on the header or something like that, and you ignore those fields. They're formatted completely differently. They have to be interpreted in a completely different fashion. And so if you think about the issue then that comes up, it says, okay, we've got this infrastructure out there that knows everything about IPv4. How are we going to transition to IPv6, a completely different technology, as far as the routers are not concerned? Certainly the wires, you can reuse the wires and everything like that, but these routers and stuff like that all have to be changed. They all have to understand IPv6. So if you think about all the routers that are in North America, or just even on the UBC campus, you can say, let's just even look at it from the perspective of UBC. What would be the challenge of on, next Monday saying everything switches to IPv6? Well, that would imply that over the weekend, if you just want to do a switch like that, that would imply that over the weekend, they went out and they found every single router that knew about IPv4 and replaced it with one that knew about IPv6. Not very likely. Okay? And now that same issue exists across all of the existing networks. So now you have this issue where it says, well, how am I going to migrate my existing IPv4 network into one that's IPv6? And one of the ways that they do this is they get routers that actually know both protocols. They often call those, I think, dual-homed routers. So they know both IPv4 and IPv6. But if you just drop an IPv6 router into a, well, let me draw a little picture. Okay, so let's say this is UBC, and this is SFU. Okay. And we've got BCNet in the middle. Okay. And right now, they both understand IPv4. And so if you send a packet from UBC to SFU, everything is honky-dory. They can talk to each other. Well, suppose that UBC decided it wanted to change to IPv6. So we're IPv6 here. Well, that required, first of all of us to change to IPv6 inside, but it also required all of BCNet to change, and it would also require SFU to change. Okay. So even if SFU changed to IPv6, right, if BCNet doesn't change, it doesn't help us. So you have to come up with sort of these bridging solutions and technologies and stuff like that for it. So they build what are referred to things like overlay networks. So for example, they will have IPv6 here, and then they'll build what's called a tunnel. They will essentially establish an IPv4 connection across like this. And then they will put all of their IPv6 traffic onto that, which will make more sense probably later than it does right now. But as you can sort of see, there's a lot of challenges involved in doing this if you already have an IPv4 network in place, and especially a large one. If, on the other hand, you're in a country that was a little late to the game, so to speak, and let's admit, and you have to kind of also realize that the countries that were early to the game were sort of essentially North America and Europe. So what did they do? They kind of hogged the IP addresses. So that kind of forces other countries to, well, not have IPv addresses. So their solution is, well, we won't even go to IPv4. Right? We'll just go to IPv6. And then they have a slightly different problem, the issue that would come up for those countries, places like China and in India in particular, you have your ASs, but you typically only have a few ASs entering the country, so you only have a few entry points. And so at those particular points, you can put converters between IPv4 and IPv6. So if you don't have a big mesh of networks going through you, that you have a whole bunch of changes that you have in just a few spots, you can sort of, those are like choke points, and you can do conversions at that particular spot.
Right before you went on to the UBC and SFU, so if they do IPv6, but VCNet doesn't do it, the workaround is what you do.
Oh, the workaround, if IPv6, if both UBC and SFU do it, you put up something called a tunnel, okay, which is essentially you establish a TCP/IP connection between a router here and a router here. So a TCP/IP connection is just what you do when you do an SSH or a Telnet or an FTP, anything like that. You just establish a connection like that between a router here and here, which will go over your IPv4 network. And then what the router does is it lays its own application level protocol on the data that's going on there, and that blocks it up for IPv6 traffic, so that it's.
You're using IPv4 to use IPv6.
Sorry?
You're using IPv4 to use IPv6.
Yeah, you're using IPv4
or as a tunnel.
You're using it as a, that's right, you're using IPv4 as a tunnel to IPv6, yeah. You can also have them in the other direction as well.
So in one of these tunnel networks, if you try to send to an IPv4 address, it would just keep propagating up to the tunnel as like going through the default route?
Well, because the routing is going to be different for IPv6, as soon as you hit an IPv4 address, you'd have to separate it out. So you would never send it over this one here, because that's not an IPv6 this would only have IPv6 stuff on it. So you couldn't actually set. Okay, so just a second. I'm getting better at this. They just, I now know when they die and I don't play around as much with them and just switch the batteries out right away. So what would happen is that if you, so on your local area network, the packet that goes out would be either IPv4 or IPv6. And this is why you have to have it dual homed. If you don't have it dual, your router has to be able to tell which one it is, and then it acts on that. So if your router doesn't know about anything about IPv4 and you send it an IPv4 data, it will just ignore it. Okay. So it gets kind of messy. So this is why, at least probably in North America, you won't see IPv6 rolling out really, really fast. There's a lot of infrastructure that has to be changed and stuff like that before it can happen. And then they have to also deal with the issue of parts of networks not changing and things like that as well. Yep.
So who currently uses IPv6? Are there certain countries that only use it, or is it very popular at all right now?
I don't know how popular it is right at the moment, but I know if you go for example, if you go to Hurricane Electric, they'll show you a map of their IPv6 network. It's, when you're in a network that is only IPv4, like we are here at UBC, it's really difficult to get some sense of what the IPv6 network is really like out there and that you can do other stuff on it. So I don't have a really good sense of that. Yep.
So it sounds like there's a chicken and egg problem with, like, I don't want to switch to IPv6 before the people I peer with switch to it. So what's stopping everyone from replacing their IPv4 routers with routers that are aware of both IPv4 and IPv6 and can deal with each appropriately? So you could put in your own IPv6 capable router, and then it's there and ready as soon as your peers have one.
Well, it's money. I mean, it's a very simple answer. It's money. They cost more. The routers are going to cost more, right? And so the other aspect of it is, I don't know what routers. I know what a router cost. The router that the department had a number of years ago cost $50,000. So we're not talking like just a few $100 for these things, okay? So if you're talking $50,000, let's just say that's a ballpark. I don't know how many $50,000 routers UBC would have, but it doesn't take very many for that to add up to a significant amount of money. And typically when you buy those routers, you expect them to have a lifespan of I don't know, whatever our lifespan is, 10 or 15 years or something like that. So you're not in any hurry to replace those, simply because of cost.
Firmware upgraded capable of letting them understand IPv6 then?
That's a good question. Having worked, not in that industry, but in other industries, they would charge you an arm and a leg for the software upgrades, right? So they're going to get even if the hardware is capable, they will get you for buying the software, right? They're not going to want to lose their money. So you might be able to save a bit by reusing the hardware, but they'll probably charge you a lot for it. Yep.
This is like a sort of open-ended, but why did it make? What was it? Do you know the decision why they didn't make it backwards compatible?
No, I don't know why they didn't make it backwards compatible. Probably has something to do with address. Well, yeah, I don't know. Okay, a better way for me to say is I don't know why they didn't make it address compatible, and the reason I don't know is because I don't know what the issues are that would have prevented that. Okay, I suspect it's just simply the fact that the address space is not. There's probably one issue is the address space. You want to expand the address space, so the question is where would the existing addresses fit in that, right? And given the fact that there is no, as we've seen, there's no organization to them. Like, so for example, if all of the IPv4 addresses were in North America, you might be able to have made it backwards compatible by just saying, oh, well, everyone from North America will just have these starting or ending addresses or something like that, and give us a, we put on a different prefix, but given the way that they're all over the world, that's probably part of it too. Okay, so a little digression there. So let's move on. So the question, having said that, and then I back up the slide, the whole reason that we talked about these things was because these different authorities had collections of IP addresses, and if you wanted an IP address, you would go there and you could, if you were big enough and stuff like that, you could go there and you could get IP addresses when they had them. Okay? So, which leads into the next question is, okay, well, you didn't ever go to one of these places and get an IP address. And you have your laptops and your cell phones and everything like that, and you go to coffee shops and all of those sorts of things, and you're probably pretty sure that you don't have just one IP address for your machine, that it probably is changing and stuff like that. So how does your machine get an IP address? Okay, so because we need that to be able to figure out where you are. So that's what the next little part is about. So the way that you do that is you use there's a protocol called DHCP, Dynamic Host Configuration Protocol. Okay. And it's a request-response protocol. And that's sort of like assignment A1 would be classed as a request-response protocol. So I just want to quickly explain what a request-response protocol is. So request-response protocol is where we have two entities involved. One is designated the client, and one is designated the server. Okay? And the one that is and what happens is the clients make requests of the server, and the server answers. That's all a request response protocol is. So question, answer, question, answer, question, answer. And it's never the way that it's question and then question back to the other guy. Okay, it's always question, answer, question, answer. So it's very symmetric, or not, not symmetric, but it's very fixed in what happens. And then just to put some more formalism on things, so that a protocol is just a set of rules that specify how these two parties are going to interact. Okay? And when we talk about this with respect to computer networking, they're actually very precise rules. They say exactly what you're allowed to send. They even tell you how you have to send it, like how many spaces there have to be between things and stuff like that. What the encoding has to be. Are you supposed to encode this in ASCII? Are you supposed to encode this in, something else? Anything like that. It specifies right down to the bit what's supposed to happen with it, and it also defines how to respond. So in your assignment number 1, right, if you type a command or you send a command to a dictionary server that's not listed in that protocol, it's a good question. I don't know what it does. I presume it responds with something that says that's not a command or something like that. I never actually tried that part on it. So you would send back something that said that. There are other protocols that if you don't actually send them a valid command, they don't actually do anything. They will just suck it all up and just turf it out and not tell you that anything wrong has taken place. So how they respond, and that's defined by the protocol. So you can't assume anything about how something is to behave. Right? So in this model, a client sends requests, server responds with answers. And why this so in the picture that I have up there, it's very, it's very straightforward, but as we'll see later, this can get very complicated, right? What happens if how quickly is the server supposed to respond? Is it supposed to respond immediately? Well, what happens if it doesn't respond immediately? If it doesn't respond immediately, how long should you wait? And things like that. Those are all parts, those are all things that make implementing these protocols a bit challenging. Other things that can make it challenging are, how big is that response going to be? Usually the requests are reasonably well bounded, but responses can often be quite long, and they may not tell you how long they're going to be. So for example, in HTTP, some types of responses, they will actually tell you, I'm about to send you 4,000 bytes. In others, they don't tell you anything. And so you have to be prepared to try and figure out, well, when is it over? When is that one thing done so that I can go on to the next request? Because HTTP is also one of these request response type protocols. Okay? So those are just a couple of the issues that can make these types of protocols interesting and challenging. DHCP, on the other hand, doesn't have that issue. Okay? So it's actually everything is much more well defined in it. Okay? So DHCP is actually a relatively straightforward protocol. So we have a client and we have a DHCP server. In particular, we have a client that doesn't have an IP address. And it's now attached itself to some network. So when you're in here and you're wanting to join the wireless network, that's one way. It's probably easier to think about this as you plug yourself into a wired network someplace. Okay? Conceptually, the wireless is exactly the same. There's just a little more wireless stuff happening at the physical layer there to figure things out. But if we look at this from a wired network, we have our laptop, and you take it home, for example, maybe, or in my case, I take my laptop into my office, and the wireless is not particularly good in my office, so I plug it into a port in the wall. And so how do I get an IP address? I don't have one yet. Right? So what happens is my client will send a message out that's called a DHCP discover message. So it'll send that message out. In particular, what it does is it broadcasts it. So it turns out that there is an IP address that is called a broadcast IP address. And it's 255, 255, 255, 255, so all ones. Okay? You broadcast that out, and if there's a DHCP server, it will get it. So what you need to know about broadcast addresses is that if a message is sent as a broadcast, that means that every machine that sees it will accept it and move it up the protocol stack. So in this particular case, for something like DHCP, it means that every machine out there would grab it, that hears it, would move it up their protocol stack, and then, so it goes up to the network stack, and it would say, get to the network part, say, 255, 255, 255, that's for me, okay? And then what it would do is it would move it up to the transport layer, and it would look at there, and it would say, okay, what process do I move this to? Well, it turns out that the DHCP protocol is always supposed to run on port 68, okay? So it looks to see whether or not a process is actually hooked up to port 68. If it is, it sends it up to that process. If it isn't, it just drops it. Okay? So when you do that, so now you've got the broadcast out there, it's gone out, and now it's gone only to those machines on that network that can understand DHCP. Or, well, it went to all the machines, but I mean, it's now percolated up into a piece of software that now understands DHCP. And so what it does, the DHCP software, is it looks around a little bit and it says, well, should I give this machine an address? Okay. And usually what will happen is if you have, let's just talk about a single DHCP server. Okay. If there's just a single DHCP server, which is sort of typical, it will look in, it will say, okay, well, who have I given out address? So it'll have a pool of addresses that it can give out to people or give out to machines. So it has this pool, and it will select one that it hasn't given out. And then what it does, once it's selected one, it goes and it says to this machine here, I'm going to offer you this address. And it'll give an address to that machine. Okay, and says, you can use, basically it means, if you want, you can use this IP address. Okay? So we do an offer like that. And now the client has to decide whether it wants to accept that offer.
If the client doesn't have an IP, how does the server send the offer to it?
Okay, so well, there's another broadcast involved. Okay, so it gets broadcast back again, so the response is the broadcast, and so all the machines are listening to it, and you get the same thing going back the other way again for a broadcast. Okay, you're not convinced?
There could be other things that accept the offer, though.
Ah, right. Okay. So there could be other. Okay. So right. So you're thinking about the scenario when, well, what if there are a bunch of machines that do this simultaneously? So how do we sort of figure that out? Well, it turns out that when you make a request, you put a unique number as part of the data fields, well, unique as in quotes here, okay? You try and make a guess at a number that will be unique, and you put that into one of the fields of the DHCP discover request. And then when they make a DHCP offer, they make sure to put that in there so that if there are two machines doing it at the same time, they'll both get offer. So you'll get the two offers, and you say, well, which one is mine? And you look at that number and say, oh, that was mine. Okay. Now, the fellow right there had a same question, but he's not. You had a question too, or was it the same question? Okay. Yep.
Is MAC address used to partake with this?
So the question was is a MAC address used for anything at this particular point? This is one of those situations where if you actually go and look at this with Wireshark, the answer appears to be yes. But if you go and look at the specification, the answer says it should be no. So there seems to be maybe some optimizations that different implementations are doing. I'm going to show you some traces in a moment of real live ones so we can talk about that.
So the thing with multiple people getting the same DHCP offer, I was wondering whether it's possible for two computers to be assigned the same IP by accident. If it's a random number, depending on how if it's just like a 4 number.
You mean that both clients decide they're going to have the same random number?
Let's say two people do a discover. Yeah, is it possible if they give the same random number? What happens if you have two computers assigned the same IP?
Sorry?
Can you get two machines assigned the same IP address?
Well, in theory, you're not supposed to be able to because, remember, the offer requests are going to come up the protocol stack, and one will definitely be before the other. Okay, like when they come off the wire, they can't arrive simultaneously. Although conceptually, you stand back and you say, oh, that machine and that machine sent something at the same time. It turns out that the way all of these things work is they actually have to be one after the other, although they can be in either order.
Yeah, but the response will come back to both of them.
Right, but that's that number then that distinguishes that.
So that's never the same?
That's never going to, well.
Practically.
I'm not aware, okay, I don't know what the precise algorithm for that is, but I do know that if you use your MAC address, it's guaranteed to be unique. So they probably hash that and something like that and then make it very, very small. Keep in mind that for that to be an issue, they have to be two of them essentially at exactly the same time picking the same number, which is pretty unlikely, but not impossible. Okay? And as there are a number of parts of computer networking that do pretty unlikely but not impossible type things. So for example, I'll give you another example of that. So when you have, when you have a wireless device or a wired device, and they're going to send data, what they essentially do is they listen, and if no one's talking, they send. Okay? Well, nothing stops two of them from sending at the exact same time. Right? So if they send at the exact same time, you get what's called a collision. And they can figure out there was a collision because they listen, and what they hear is, instead of hearing what their traffic was that they were sending, they hear it now mangled with something else. So they detect that there was a collision. So then what do? Well, if they both waited the exact same amount of time and did it again, you'd just have another collision. So what they do is they wait a random amount of time, and then they do it again. Well, in theory, they could all pick the same random number, and in theory, right? And then transmit at the same time again, which is fine. Okay, collision. They both detect collision. They apply the same algorithm again, which is, oh, it didn't get through. Wait a random amount of time. Try again. So in theory, they could always be, each of those could be picking the same random number, and no progress would be made. In practice, that never happens. So you're playing the odds on a number of these things.
So there are mechanisms in place to detect collision, then wait.
Sorry?
So there are mechanisms in place to detect collision, then wait and do it again.
Yep. So they detect the collision, they wait, and then retry. Yep.
So with the unique number associated with the discover, is it enforceable that a client can't take an offer that's not theirs?
Is it enforceable? No. The client could take one that's not theirs. Okay, so this is one of the things that you've highlighted. One of the very interesting things about computer networking is that because we control and write the software, if we wanted, we could sit out there, listen for offers. We could write some code that listened for offers, and whenever we saw an offer, we could start using that IP address. Okay, nothing stops us from doing that. Right? Other than the fact of the goodwill of all of the people who have written this software.
So in that case, what does the original client?
In that case, well, what happens in that case is you usually get a message showing up saying something along the lines of, 2 machines appear to have the same IP address, and I don't know what. And usually one of them gives up at that particular point. So, yep.
Is it also possible for there to be 2 servers?
Sorry?
2 servers? Like,
There can be 2 servers. Yeah.
and then fight.
No, if there are 2 servers, okay, so what would happen in the case that there were 2 servers is that they would both see the discover request, they would both make an offer, but if you put 2 servers on your network, okay, like as an administrator, you have to make sure that those 2 servers are going to hand out IP addresses from different pools. Right? So maybe one would do pools from 0 to 100, and another would do 101 to 200 or something like that. So you just make sure that they don't offer from the same pool. And then what happens is they both make offer requests. So now your client would see 2 offers. And it can then just, so this brings up the next point. So what does it do next? How do you know which one you want? Because if you're the server, you want to know whether or not the client decided to take your offer. Right? You made an offer, but because there could be more than 1 server out there, right? If there were 4 servers out there, you don't want 3 IP addresses saying reserved and 1 only being used. Those other guys want to know, hey, no one wanted that IP address, I can reuse it. Okay? So what happens is now you make, it's bizarre terminology, you make an offer, and then what you do is you send out a request and say, I want the IP address that you just told me I was allowed to have. Okay? And so you do that, and hopefully you get back an ACK that says, now you can start using that IP address. And if any of those packets get lost along the way, just redo it. Okay, so for example, if the discovery packet is lost, Well, you're not going to see any offer packets. So because you don't see any offer packets, you just sit there, and after it's about 2 or 3 seconds, you try again. You make another request. Okay? And if they had actually, since you can either use the same sequence number or the different sequence number, it doesn't matter, or identifier number, they would know whether or not to give you back the same IP address. Okay? And so that's it. That's DHCP. Okay. Yep.
Is that second call from the client also a broadcast?
Yes, because, well, this is one of those things where you, okay, so why does it need, it doesn't, technically it doesn't need to be a broadcast because it knows the IP address of who sent it the offer. However, to deal with the problem of multiple servers that are out there, that request going back as a broadcast is saying, okay, I'm basically saying I want this particular request. And so it lets those other ones that it's not going to accept, they can sort of see, oh, you know, that host that had request 4,532, it didn't take my offer. It's taking someone else's. I feel jilted about that whole thing, and so I guess I will hand those IP addresses out again. So, okay. So let's, oh great, okay. This might be a bit of a challenge for me. Okay. So what I have here is, this is a Wireshark trace. So if you haven't played with Wireshark, it's always a blast to play with Wireshark, or scary, depending upon your perspective of the world. Okay, so I'm going to turn the lights down, I think. Since some of those, whenever you change the lights in the room, it turns the microphone off. So sophisticated you, of course, right? That's completely obvious. It should do that.
What happens if the DHCP server runs out of IP?
Oh, then it won't offer anything. Okay. Okay. So here's an example. This was a trace done on a little bit of a network here. So these are times going down here. They're not in seconds. I believe they're in milliseconds or something like that. Or no, maybe they are in seconds. Okay. So what we have here, these addresses here are MAC source addresses. Okay. And these are destination addresses. And so you can sort of see here that it's doing a broadcast. It says broadcast. Those are ones how it does. There's another broadcast one. Okay. So as you can see, there's a bunch of traffic going on. So what I'll do is I'll just say, let's just focus on the DHCP ones. Okay. So those are just the DHCP messages that go out. Okay, so what we have here is we have our source machine. It doesn't have an IP address yet, so it fills it in as zeros. And it sends a broadcast message out, DHCP, and it says that's a discover message. Okay? And it actually turns out that it does another discover message, separated by, as you can sort of see, about 2 seconds there, or 2 seconds and a little bit. And that turns out that if we go back and look at the trace, what's happening for the first discover, it's a little bit weird. Okay, so one thing you have to know, one thing about DHCP is when you make your discover request, as part of the data in there, you can ask for a particular IP address. Okay, so you can say, you know, I'd really, really, really like you to give me this particular IP address. And what normally happens, you know, if this is on, for example, your home network or something like that, or say in my office, you'll probably get it. So they'll give it to you if they haven't given it out again. Right? So it's got its pool of addresses. You say, I want this address, and it'll look and say, oh, no, I haven't given that address out to anybody, so yeah, I'll give it to you. Okay? So what's happening here is it does a discover, and then there's a few seconds in there where it's trying to figure out whether A, it's actually given it out, and even if it has given it out, it's trying to figure out if there's actually anyone on the network who might be using it even though it didn't give it out. Okay, so it's just trying to be really, really safe that the IP address that it wants to give out isn't in use. So it does that. And then we get another discover again. And so you'll notice here on the very end, that's the ID that the client selected for the request. That's the one that's being matched on. Okay, so we do that, and we get the discover request, and then we get, now this is where it gets weird. Okay, so it says the source is 172.16.3.1, so that's the server. But the destination, according to the spec, should in fact be 255.255, should be a broadcast at that particular point. But there appears to be some liberties that can be taken, and they fill that in with the target IP address that you want to give them. Okay? So now you should say, well, I don't have an IP address. How do I get it? Well, this is where link layer or MAC addresses come in. So at that particular point, if we look back to the discover request, oops, there, and we look at the Ethernet frame down here, we'll say, here's my source MAC address. That one down there. And if we look at this one here, you'll see that the destination is in fact that address. So what happens is that it comes in, so that machine grabs it because of the MAC address, says, yep, that's for me, and then it goes up the stack, realizes it doesn't have an IP address, and says, and growls around and figures, oh, this is something I need to respond to or work with, so it does the offer, and then it doesn't start using it yet, and then it broadcasts back that it's willing to accept it. So if you sort of look down here in the Bootstrap protocol part, you can sort of see the transaction. It's called the transaction ID, and you can see what it's going to use it for and everything like that, which one it's accepting. But what's interesting about this as well, when you make an offer, oops, didn't do that quite right. When you make an offer, one of the other pieces of interest, we've got a host. You can be given a host name, so they could tell you what your host name is going to be. And down in here someplace, the two things of interest. Okay, so there's this renewal time says you're supposed to renew this address in 30 minutes. So they tell you how long you're allowed to keep that address. And if you're not supposed to keep it longer than that. Okay, so you do that. So they tell you how long you can have the address. They tell you who your name server is. Okay, so what host your name server is. And they also tell you your default router, where you should route everything to. So this is done on a home network. So on the home network, it turns out the little home network that I have has got a name server on it, and it is in fact the router as well to go to the rest of the world. Okay, so that's why everything is set up like that. No, oh.
So I thought the DHCP offer from the server to the client was identified by the client based on the unique ID,
yep.
Transaction ID.
Yep, on the end.
The MAC address.
Sorry?
But then you talked about the MAC.
Oh, so the MAC address is how do we actually, okay, so remember what's happened is the packet goes out, but it has to actually get to the machine before the machine, and it has to work its way up to the DHCP application before it can check that transaction ID. And so the MAC address is the thing that gets it to the machine. Okay? You could broadcast it as well. They're not broadcasting it in this case, but you could also broadcast it. Yeah.
If I know the range of addresses for the network that I want to connect to, can I manually enter an IP address and not go through DHCP, or?
Well, okay, so that matches up with the question over there about the other one. So the answer is yes, you could. What would happen at that particular point, though, is first of all, you might not know some of that other information. Okay, so you might not know what the router is and the DNS servers are and stuff like that. So you have to enter that as well. Okay, and if you happen to choose an IP address that someone else is using, then there will be some potential problems. And just because you choose it doesn't mean that they won't then proceed to hand it out later.
But if I enter all of it correctly and I choose an address which isn't taken, I don't, like...
If you choose an address that isn't taken, if you're lucky, it will work for a while. If you're unlucky, it will stop working right away. But the only reason it's going to stop work, the reason it may not work is because you can have rules in your router that say if I haven't handed out an IP address, you're not allowed to route to it. So they'll just say, nope, no one's allowed to route to it because I haven't given that IP address out to it yet. So that could be one reason. And the other is, well, it may not go through the step of trying to detect whether or not that address is in use, and so then eventually give it out on you. Right? So it's not a, we would term that as a hack, right? So it's like, you do sometimes do things like that when you're debugging and trying to figure things out, but you kind of want to play by the rules if you're not doing something like that. And I want to just show you one other thing. Okay, so there's something called ARP, which we'll talk about, is called the Address Resolution Protocol. We'll talk about that more later on. But basically, as you can see there, what it's doing, if you look on the right-hand side, right after you get a discovery message, right? Okay, you've got one here. You see this message that goes out. It says, who has 172.16.3.107? Tell 172.16.3.1 whether or not if you have it. Okay? So that's in this particular case, what it's trying to do is trying to figure out, is there someone on this network that's, I'm about to, in this particular scenario, what's happening is the DHCP server is decided, I'm about to hand out this .107 address. Is there anybody out there who's using it? So they're trying to avoid the problem I just described for you. Right? And they're saying, okay, if someone's using that, then I'm not going to hand it out. If no one's using it, then I will hand it out. That's the one I've chosen. And so there's a little bit of a check there to try and avoid some of the problems that I outlined with the scenario that you had. Okay. Okay, so any other questions about that? Yep.
But if you are trying to contact an address, why don't you just contact the address directly instead of broadcasting it? If someone is using them, they will respond.
Well, you don't know that they'll respond.
So if they don't respond, can you just assume that it's not?
No, it could just mean that there's no application there that knows how to respond. Right? There are no protocols that you know that every machine is running. So there's no, except for something like ARP. But ARP is not so anything else that you do, you can't guarantee that there is something there. So there's only a few ARP is one of the few that they all have to have. So that's essentially why you do something like that, really, really low level. Like if you think about it, like not every machine has an HTTP server, not every machine has a time server. So what application would you contact? Right? So you have to have something that everyone has agreed they will be running, and so it turns out that they sort of make use of this because you need it. It turns out we need it for some other reason as well. Okay. So now, before anything works, I have to get my mouse back over here. Okay, so just sort of leave you with this last question, or well, not the last question, but a question for next class is, okay, does all of the traffic have to always go through a router? Okay, or can you actually get data from one machine to another without having a router involved? Okay, so that's sort of the next step with this. Okay, so we'll talk about that on Monday.
Yeah, I merged this. So if testing that, right? So like you should be able to have a connection there. We've got to figure out how to probably writers. But looking at it, and then like, so just have one, second hand, or if it's like you make a few lines, I don't know. I added in all the, basically, added in for every command, for all your